So I realized that I forgot what I promised you. Specifically, I wanted to show you how you get those long names for the structure variables. Pardon me. So now I'm going to show you because the variables are still there since I did not shut down MATLAB. So if you look here, so when you click on it, it won't show up the first time. You have to run the program for it to show up in the MATLAB workspace. But then if you double click on it, it gives you a pose and a covariance split. Let's go to the pose. And then it gives you within pose, position and covariance. And notice the structure is being revealed here more and more. If you go to position, then you have pose, position. Here are the XYZ positions. So obviously the X position is odom.pose.position.x. So that's how you figure out how to get those structure variables, the data structure. Now what about the other part, the orientation? Well, that's going to be a mystery right now because first of all, this XYZ has nothing to do with position. It's part of a 4-element representation known as the quaternion. And the quaternion is used to represent an angle. And the reason for that will be evident tomorrow because you can't use angles because one problem is that they wrap around and that causes a problem. So the quaternion, there's a guy called Hamilton, famous mathematician, who came up with this quaternion notation in order to deal with angles. So that's what this is. XYZ is not related to the other XYZ. So XYZ, W, 4 numbers constitute the quaternion and the angle information is in there. It's buried in there and we'll find what that is tomorrow. Yeah, VLMSD, is it still there? Yeah, here it is. So linear, XYZ. These are the velocities in the 3 directions. So you click on X, and that's the full variable. And you go to angular, and you get 3 more variables. Because you can rotate here, you can rotate this way, and then you can rotate this way. Though of course, for a robot on a 2-dimensional surface, only this is the. If you rotate like this, robot is going to fall over. If you rotate like this, robot is falling over sideways. So you won't need to use the other 2. This is meant for any general object. So for a drone, all the numbers will be active. So I wanted to think about this problem that I'm going to outline, and maybe we'll get to it later this afternoon. So this is the cursive C. Cursive handwriting is an art that is almost lost now with computers everywhere. Nobody knows how to handwrite, but this was the cursive C. So if I ask you, can you drive the robot on this path? Now that's just like any path, right? It could be a path going through campus. But I'm using this as an example. So it could be like you're patrolling at night. The robot is autonomous, it's going through campus, but maybe this is the path. How can you use your knowledge that you have right now to drive the robot through that path? Well, the idea is that can you think of it as pieces of circles?
Yes.
So in a very rough way, we don't want to be exact, but maybe I have one circle for all of this. You see, at that point something seems to change. So maybe a kind of a semicircle here. So you can always go back and change it, right? If it's not a semicircle, if it is 40% of a circle, yeah, you can go back and change that. Because remember the time? You can run the circle for different amounts of time. You don't have to run it all the way through, or half of it, or 3/4. It can be 23% of it. So you can adjust it later. So this is one circle, and maybe this is another circle. This is almost a straight line. then you have another circle, and a big circle, and another circle. See, different people will break it up in different ways, but you should be able to roughly break up the path into big circles, but that's not the way we drive. What we use is very tiny circles, right? Because we normally want very sophisticated control of the path. But this gives you an idea of what path planning is, you know. You can break it down maybe 7 circles, 6 circles. Now how would you go about doing that? The way you would go about doing that is to first look at your circle program and see whether you can use whatever is in there. So for instance here, so this is the main loop, right? So that tells you how to do a full circle, but TC does not have to be a full circle, right? This is the time for the whole circumference. It will be the time for maybe 15% of the circumference. That radius of the circumference is established by the velocities you pick. Right here, R is equal to velocity by rotational rate. So if you want to change to a different circle, you just change one or both of them, V and omega, to get R, right? And then you drive it for a different amount of time, because remember, not all circles have the same proportion of the circle being traced out. So then what you would do is you take your basic MATLAB program, this one. The for loop is to do a piece of the circle, not necessarily the full circle, right? You get it? I'm sorry. The while loop is to do a piece of the circle. So on top of that you have a for loop. So a for loop is typically used when you know the number of times you want to iterate something. While loop is used when you want to iterate till a condition is reached. You know that basic difference between for and while? For is for a fixed number of times, while is till some condition is satisfied. So you wrap a for loop around this, and each for loop will be doing a part of the C. You know, the C, the cursive C. So maybe 6, 7 for the for loop, and in between you adjust you have to recalculate TC, because each time you have a different amount, and you get a nice path. It's not that difficult. You can actually watch it. You can watch the robot do that, but then if you get its odometry and plot it out, then you'll be convinced.
But to figure out the values we need to give for certain radius of curvature, we'll have to do it practically and see for ourselves, right?
Right.
Many permutations and combinations.
So you can actually draw this on graph paper and get a rough idea of the radius. If you draw it on graph paper, it's actually a trial and error. It's not meant to be perfect. Initially you will miss out on a loop or something, and then you'll say, okay, maybe I should hold this loop a little bit longer. It's like practicing handwriting. That's what it is. But it's not about handwriting. It's about realizing that this is how a differentially steered robot moves. That's the whole point. So maybe we'll try that later this afternoon. Okay, now. So I showed you how to deconstruct the odom as well as velocity message. So that's how you get at those interior variables. Now looking at what I posted, let's bring it up here. So right here, we finished that. We finished introduction and the kinematic derivation, and we went through this. So now we got to go to part A. So from velocity to position part A. So what we're going to do is, we're going from our knowledge of the kinematics to come up with how they figure out odometry. So let's first do some hardware. You know, how exactly do they count the wheel rotation? So there's something known as the wheel encoder. So I'm going to pull up a picture of a wheel encoder. It's not so much the wheel encoder as it is just the encoding wheel part of it, not the whole electronics. Look at that picture, the one I found earlier, because it had much more than this. But this shows you the basic idea. So let's say that you have like a disc bonded to the wheel in some way or mounted on the same shaft. This is how they read the velocity of the shaft of any motor, even industrial motors. So you have a disc with holes, right? And this would be many, many more than you would imagine. It's not 5 or 10 or even 100. It can be 1,000 or 10,000, because it is printed literally. So imagine if you had 10,000 of those holes. Well, before I continue with that thought, you have a light emitting diode and a pickup on the other side. So as the wheel spins, If you have set it up so that the light can go through, then you can have the pickup on the other side, but you can also reflect the light and catch it on this side. So every time there's a gap or a different reflectivity surface, you will get the signal to be high or low. Is that okay? So by counting it electronically, you can have a computer that picks up those pulses and counts the frequency. And essentially, you know, if you know how many of those holes you have around, you can figure out what part of the wheel has moved, right? You can figure out what is the wheel rotation per second. So those are, this is how, you know, the rotation of any, anything that's rotating is measured. You know, all industrial machines have this. One thing I want to point out is that sometimes you have two of them that are slightly displaced. And when they are slightly displaced, then on channel A, you get a certain sequence of pulses, and on channel B, you get a slightly delayed sequence of pulses. And the whole idea of having an A channel and maybe a B channel slightly later is because by looking at the delay, you can tell whether it's going in one direction or the other. So if A is going ahead of B, the pattern might be like this, but if B is going ahead of A, it will be the opposite. So you can tell not only the number of revolutions per second, but also whether it's going forward or backward. And this is quite sophisticated because you can pick up, like say 1,000 of the tire surface, 1,000, it'll give you a tick, right? But 1,000 is not the same as 1/10,000. Neither is it the same as 1/10 million, right? You can't put an infinite number of holes there. And therefore, there is going to be some error. You can reduce the error by putting more and more of these holes, but you cannot eliminate it. And therefore, odometry is never perfect because what if, you know, the wheel is moving and it's in between two of those pulses? It's possible, right? No matter how close the spacing of the holes is, it won't be able to catch a motion in between. So it's going to say, hey, you didn't move, but you actually did. So therefore, there is a tendency for error to build up. We'll get into it in greater detail later, but error does build up. So odometry can never be used for the long term. Odometry is only good for like a few meters at a time. After that, you have to correct it. And that topic will be discussed in the localization chapter. So you need a GPS signal or some other means of correcting the odometry. It's basically resetting odometry, right? Because odometry is falling apart. So you reset it by correcting it with the GPS signal or something, and then odometry again continues in the short term. So I want you to think of this as odometry short term and a GPS correction every now and again. Because GPS is not available at the same frequency as odometry is. How could it? Because look at this. You're getting odometry every hole, right? GPS will never be available at that frequency. Therefore, GPS is used once in a while, and odometry is used in the short term. Odometry falls apart, GPS corrects it. So if you use odometry alone, you'll be totally lost. You will not know where the robot is after a while. The actual robot will be far away from what you are predicting using odometry. So I want you to think of this as something that all human beings do. So we have a rough sense of distance because we count our steps. We actually don't count it out loud, but we are conscious of how far we are moving. And then somebody has told us, look for this particular store, right? So every once in a while we look up and we try to find that store. That looking up to find the store is like a GPS reading. The counting steps is just rough distance. And we do that all the time. When we're walking down the hallway, we're doing it because we're looking at the doors going by and features going by. If you're walking to the parking lot, you're doing it. A human being is doing it subconsciously, but a computer has to do it consciously because the computer is not like a human being. So odometry is like counting steps, and the GPS is like you look up for something familiar. Nowadays, of course, with the iPhone or with any phone, the mapping capability, you don't need anybody to say, look for this particular store, because it's giving you directions every instant to get you there. So that old, maybe when your grandparents were, doing it, they would give you detailed instructions on how to get to their houses, for instance. That's no longer needed anymore. They would say, take the third right turn after the signal light, right? So in between, they'll say approximately it'll be like 2 miles from the, so that's odometry, right? And then when you find the third intersection, that is GPS. So that's how instructions were given in the old days. Okay, so let's move on to the document I highlighted, which is, pardon me, from velocity to position, part A. For autonomous robots, the differential steering system is the most commonly used. So we have built, we meaning back in my university, we have built our own robots for competitions, all the way up to about 100 kilograms. So something like 225, even 250 pounds. They're quite powerful and they're capable of going to a top speed of between 5 miles per hour to 10 miles per hour. So a human being cannot, well, athletes can, but ordinary human beings cannot run at 5 miles per hour for very long. You slow down. So it can actually break your leg if it hits you at full speed because it's quite heavy. So after that, the skid steer, right? Skid steer, let me tell you what skid steer is, you'll see pictures. So you have fixed wheels, all the wheels are fixed. In the differentially steered vehicle, the caster wheel is not fixed, right? It's capable of orienting itself. So in a skid steer system, it's like a tank. All the wheels on the right side go at a certain velocity, all the wheels on the left side go at a certain velocity. So just like a tank, if you spin the right set of wheels faster than the left set of wheels, you'll skid. Literally you'll skid. You won't turn like in a differentially steered vehicle or in a regular car. You will literally skid on the ground. So that's why it's called skid steer. It is rough on the tires because if the ground is rough, then the tires will wear out faster because it's literally turning while skidding. Also, you cannot use encoders and odometry to localize a skid steer system. Does not work. Because that skidding motion, if you do the same operation twice, it might end up in a slightly different orientation. Now how do you deal with that in the real life? Because you have a human being in the loop. So if you skid too much, he's going to skid back into the right position, right? And it's set up so that it's easy for a person to do that. Like, you learn how to drive a skid steer vehicle. But for the computer, if you're going to depend on odometry, that's not a good idea because the skidding is going to record encode accounts that have no meaning. It's the nature of the ground, right? The skidding is going to be slightly different. So skid steer vehicles never use odometry. Instead, they use something known as an inertial measurement unit. So there is a topic at the very end of this sequence of topics on sensing and perception. So you will see what that is, IMU in greater detail, but I'll give you a quick synopsis of it. So an IMU at the very least has an accelerometer, a 3-axis accelerometer. That means acceleration in this plane, this one, this way and this way, right? So if you have acceleration, and let's say you integrate it, right? Let's say I integrate it, right? I can get position in the 3 directions, right?
Yeah.
And then if I integrate it, I get velocity. And then, I get velocity when I integrate once. And then when I integrate twice, I get x, y, z as a function of time. So just by triple integration, or double integration rather, I can figure out x, the position as a function of time. Now you say, okay, I've got a perfect system. Why don't I use an IMU on a differentially steered vehicle? You can, but even an IMU, if you use it for too long, you will get lost because there is noise. The accelerometer is not a clean device. It has noise on it. So the genuine acceleration has noise imposed on it. So any practical measuring device has signal and noise, right?
So noise as an error.
As an error, yeah. And it's a random. It's a probabilistic distribution. So what happens is, if you integrate for a long time, you'll find again that you're lost. So it's something that skid steers have to use because they can't use odometry. Differential steering vehicles can use either one of them. Ultimately, you need GPS or some other form of confirmation. So that's the part. You have to look up and confirm where you are. Correct your errors. So So both of them need correction. So we need to derive the odometry equations. What we have right now is the velocity model, right? The velocity model says I'm on this circle. So the velocity model is looking into the future. The odometry model is going to be looking into the past. After you have moved, it's going to use the odometry readings to figure out where you are. They are both linked because they both use the same set of equations at their core. But odometry is after you have completed the motion, velocity is predicting into the future. So when I say I've got V and omega, and this will give me a circle R of radius d by omega, I'm saying, okay, that's what should happen if I start driving it, right? But odometry is different. I'm going to collect data, assuming I'm on a circle, and then I'm going to say, if I'm on a circle and I've got this data, where do I start? So I'm going to take the circle backwards and say that's where I started. So let's see how that works. So let's go find the position model now, which is the odometry model. Alright, so remember these equations? This is where we left off in the morning. Psi I dot is equal to R theta inverse, that's the transformation matrix. And this is V, and this is omega. And again, here's a reminder that V1 is actually V right V, and V2 is V left V. And 2L, there is a term for it. The spacing between the wheels is known as the track of the vehicle. That's the technical term given to the spacing between the wheels. Even regular cars have a track. Wheelbase is different. Wheelbase is front to back. The spacing between the front set of wheels and rear set of wheels. Track is side to side. So we've already gone through this. That basically if I change V and omega, I can get very sophisticated paths. This is what this set of bullets is saying. Different combinations of V and omega will give you different circles, right? And then one choice might be better than another. That's the whole game, isn't it? I mean, not all paths are the same. If I say get me there as quickly as possible, then there are very few competitors, because there might be any number of paths, but some of them might be too slow, or you're turning back and forth too much, right? But others might be faster, so that's the reverse kinematics problem. Solving the reverse kinematics problem is where the money is. Solving the forward kinematics problem anybody can do. So you have to make a choice. But you also have to make sure that you remain below the speed limit. I told you that we can go up to 0.4, 0.22 is the turtlebot 3's actual limit. You're going to bring the turtlebot 3 later, right?
Yeah. He's just not.
Okay. So you can go up to 0.4 only because it's a simulated turtlebot 3. The actual turtlebot 3, I don't know whether you can drive it at 0.4. So the point is, imagine the robot moving through a field of obstacles, right? So you have to give it different little tiny circles to get it through. That's what we do when we drive. We are actually creating little mini paths, right? But we do it in our head, having learned to drive, being humans. But a computer has to be taught all these things, how to create a path. Also, remember those circles? They are not the real circles. You remember my figure of 8? Those circles are not the real circles, because whenever you change speeds, there's going to be a transition period between one circle and the other. That's what is called dynamics. And in the real world, you have to worry about dynamics. You can't just assume that you have a pure kinematic model, because there is no pure kinematic model except when you have a lot of torque in the motors and the robot is very light, or a combination of both. So otherwise, kinematic models are not enough. So we basically went through all this. So I don't have to say anything more. And this is a nice test to figure out, have I understood what a differentially steered vehicle is? So we can go through this. Let's say you have the wheels spinning at equal forward or backward speeds, right? Do you agree the robot path is a straight line? So if you have the right wheel and the left wheel being driven forward or backward at the same speed, then the robot path will be a straight line. And the radius, we said, was infinity, right? A straight line has infinite radius of curvature. These are equivalent terms. Let's just go with instantaneous center of rotation. what will be the ICR at infinity? Because it's a straight line. So the center is off at infinity. So wheels turning at constant but different speeds. Robot path is circular, fixed radius of curvature, correct? V by omega. Radius of curvature can be positive and negative. You know what that means? This is positive radius of curvature. I've never seen this in person. Can you believe it? Somewhere in the building we have one of these, but I never encountered it. Our life never intersected. So you can see it's quite small. Put it down here.
This is the turtle bot 3.
This is not a meter. This is a foot, right?
Yeah.
See, I said foot because of habit. We still deal in feet in the US. So a meter would be something like this. So it's going to take 5 seconds to go from here to here at maximum speed. So the simulation will be quite slow. So that's why I said speed it up to 0.4. So can everyone see it? Maybe we can pass it around. But it has a LiDAR here. So all these used to be quite expensive. But the prices have come down. All electronics products are like that. The TVs today, the prices are amazing. You know, a TV that was $3,000 is now selling for under $500. So it's quite nice. You can take a look. See the advantage of that. You can take it to your room and you know, put it on the floor and try out stuff. That's why it's small. I find its low speed a little bit irritating because the previous Turtlebot 2, the maximum speed was 0.6 meters per second, almost 3 times this. So everything would go faster on the gazebo screen. Okay. So, what's the difference? How do you get positive and negative radius of curvature? So if V and omega are positive, right? R is positive. So that means you're going like this. See? This is the positive angle direction, remember? Counterclockwise. So, positive radius, right? What are the combination produces a positive radius? Minus V and minus omega, right? So what is minus V and, because minus over minus is plus, right? So what does it mean? It means you're going backwards, right? V minus is going backwards. What is omega going, omega negative? You're swinging this way. Makes sense, right? If you're going backward and you're going this way, you're going around the same circle, right? This way. And then you can figure out the other two, plus and minus and plus.
So the radius cannot be negative.
What?
Radius of curvature cannot be negative.
Radius of curvature, I'm glad you asked that question. So radius, in the traditional mathematical sense, cannot be negative, right? Here it can, it has a meaning. The moment radius is negative, it means the ICC has flipped over to the right of the robot. So in robotics, minus R has a meaning. It means the ICC went from here. So I was going like this, ICC was here. I turned this way. The center of curvature moves here, right? The radius is considered to be negative. So that is the meaning of a negative radius. Okay, wheels turning at the same velocity in magnitude but in opposite directions.
Yes.
So wheels turning in the same physical rate. One is this way and one is this way. You agree the robot is spinning in place. The radius of curvature? 0. And the ICC is right here. It's directly below, remember the point in the middle of the axis is right down below that. One wheel stationary while the other rotates at constant velocity. Huh?
Rotates around the contact point.
But the point will be the stationary wheel.
The wheel that is stopped, the radius, the center of curvature is below that. You agree? The center of curvature is directly below that wheel. What is the radius? It is 2L.
2L.
2L will be the radius, right? It can either go this way or you can stop this wheel and make it go this way.
Yeah.
So this is the Pioneer. The figure of 8 came from this vehicle. It's actually shows a lot of dynamics effects. It's quite heavy. It's about 40 pounds. And the motors are good too, but see, it's not the motors by themselves or the weight by itself, right? It's the motors in conjunction with the weight. So for the weight, the motors are strong but not strong enough to overcome dynamics. So that's why you get that figure of 8. That lazy behavior, right? It doesn't immediately jump into the new circle, it gradually, I call that lazy. So that is what dynamics is about. Okay, we went through the 4 cases. V omega, positive, positive, negative, negative, positive, negative, negative, positive. And we went through this. I don't know, maybe I should change my style because I feel I talk and then I feel that I find that the next few slides are actually what I've talked about. So maybe I should advance the slides and then talk. So basically I've said this also, that complicated paths can be thread together by little tiny segments of circles. Okay, now the main thing is the odometry equations. How do I do the odometry equations? Let's see. So this was the first equation. X dot of t is equal to, so x dot of t is on the global axis. Take the forward velocity of the vehicle and project it using the heading angle. Remember this? I just separated the matrix equations into the three again. We got the matrix from the three, now I've gone back to the three separate equations. So x dot of t is equal to v of t cosine theta of t, which is v1 plus v2 by 2. Remember, v of t is actually the average of the two, right wheel, left wheel. One is right, two is left, and here's the reminder. v1 is vr, v2 is vl. Cosine of the heading angle. The heading angle in general is a function of tan. Y dot of t is equal to, now wait a minute, the robot cannot move sideways. Why am I worrying about y dot? This is not y dot for the robot. This is y dot on the global axis. So on the global axis, of course, you can have both x dot and y dot, right? You can be going like this. So v1 plus v2 by 2 sine of theta of t. Theta dot of t, remember, omega is equal to v1 minus v2 by 2l. So I just deconstructed the three equations again. Now, maybe I can convince you, but I'm going to give it a shot. A closed form solution is a solution where you get an equation. That means you can integrate this, right? I told you it's not possible. In general, it is not possible. In general, it is not possible to get x by integrating this. Only in two cases can you get it. We're going to go through those two cases. One is straight line motion, and the other is circle. But in general, you cannot integrate this. Because why is that? Just look at it. You're saying, I know the integral of cosine is sine. No, but that's only if this is in the form of constant times t. This is not cosine 3t, is it? Something like that. This is cosine theta of t. So you cannot integrate it. You can integrate cosine of 3t, right? You get sine 3t by 3. That's not what this is. This theta of t is related to v1 and v2, which are coefficients of the first equation. So there is a coupling between these two equations, right? So because of that coupling in general, you cannot integrate it. It's impossible to integrate it because theta depends on this, and v1 and v2 are involved here in the two places. And the velocities are in general time varying. Each moment I can change the velocity. Velocity is not a constant. It can be. The special cases will come from assuming it to be constant. Right now, it can be anything. Equations are interdependent. Velocities are time varying. So, special cases. So here's one, robot driving straight. Now this is a useless result. We're just doing it because, mathematically we try to explore the possibilities, but the result is useless because if a robot, so what does it mean, robot driving in a straight line? It means if this is the heading, you never get it to steer. You go up and, so only if you have a petrol job that requires you to go up and down, it's useful, right? Otherwise, who's going to get a robot to move up and down a line? That's not going to be very useful because the heading is fixed. Remember, heading was angled with respect to the xi axis. So whatever heading it is, that's it. You cannot change it here. So theta dot, right, is Vr minus Vl. Remember, Vr and Vl are equal. Straight line motion. So theta dot is 0. So theta of t is a constant theta naught. That's what I meant by constant heading. That means whatever is the initial orientation, it will maintain that. And that is brought about by the fact that both wheel velocities are the same. So x dot of t, are you with me?
Yeah.
Is Vr plus Vl by 2. That is the first equation. And now instead of theta, I can put cosine theta naught. If you've forgotten, see here, this is now cosine of theta naught, a constant. So cosine of theta naught, v of t cosine theta naught. So I can integrate now. X of t, take the constant outside the integral sign, v of t dt plus x naught. X naught is the initial position, initial conditions, right? Because when I integrate this, there are initial conditions, x naught. Similarly, y of t is sine theta naught, integral of v of t dt plus y naught. Y naught is the initial position. Now, that doesn't look like a straight line, and that's because we generally don't focus, we focus on y equals mx plus c. We don't consider what is known as the parametric form of the straight line. So the parametric form you can get this way. Y of t minus y naught, right? Over here, x of t minus x naught, divide one by the other. It is sine theta naught by cosine theta naught. Do you know how I got that? Y of t minus y naught, x of t minus x naught, and divided one equation by the other. And sine theta naught by cosine theta naught constant is equal to tan theta naught. And remember, that's m, the slope of the straight line. And now you see that's the same as the regular form of the straight line. So that means if you point the robot this way, it keeps on going, in this direction. It's not really useful, but it's an interesting result. The other result is actually useful. Even though if your life is driving the robot on one big circle, that's not very useful. But remember, we can change circles, right? But the circle result leads to odometry. The circle result gives you the odometry equations. Because no matter what you're doing, you could be driving like this, it's made up of little tiny circles. And whatever result we get here can be used for those little tiny circles. So we can figure out exactly where the robot is if we can figure out the equations for each one of these tiny circles. So assume constant but different wheel velocities. Hence, circular path, equal velocities we've already considered. We don't go back to that. Circular path can also be obtained. Forget that. That's a special case. So let's get to the equations. Theta dot t is equal to v1 minus v2. Remember now, v1 and v2 are constants but not equal, right? We stipulated that equal but different, and that's what we're doing here. I'm sorry. Constant but different, right? Constant but different. So v1 is different from v2, so I can integrate. It's constant, so I'm allowed to integrate now. So theta of t is v1 minus v2 by 2l times t plus theta naught. Everybody got this? Yeah. Substitute into equations. Now this, I used to derive this once upon a time, but my students got upset because it takes 2 pages of derivation, and so then I said, if you're interested, come to my office. So once theta has this form, which form? This form. It's possible to substitute it into this equation and complete the integration. It takes about 2 pages. And this is the result you get. So you have to trust me, or if not, we can sit down and do the integration at some point. But essentially this is what I get. So that means the x and the y is some increment with time over the initial value. X naught and y naught is not the center of the circle. X naught and y naught is where the robot started. It's a point on the circle. So x naught plus y naught plus this whole thing. Now why is this a circle? That doesn't look like a circle to me. Well, let's go to this website. So this website is all about the parametric form of a circle. X is equal to r cosine t, y equals r sine t. That is the parametric form of a circle. You can have other numbers here before the t, but this is the basic parametric form of a circle. And notice that r here is actually the radius of the circle. Whatever number you have here and here is actually the radius of the circle. Here it is. This is it. So x is 20 cosine of t, y equals 20 sine of t. 20 is the radius. That is the point on the circle. That's what we are calculating on the left hand side. X of t, y of t. We are calculating this point. Given some initial point. Somewhere we have to say, okay, I start here. This is my x naught, y naught. And then I can calculate my way all the way across the circle, except I'm not going to. I'm going to have one little circle here, then I'm going to start a different circle. And the different circle is, I should have been, there is somewhere here, okay, here. Options, yeah. Don't freeze the radius. So then I should be able to drag it out. See, I can make it into a different radius. See the number changing here? The radius is changing. But that's not the point here. The point is that this is the parametric form of the circle. And whatever is multiplying the cosine and sine, that should be the radius according to the mathematics. Remember V was V1 plus V2 by 2. So here is V1 plus V2, right? So I can put a 2 here and a 2 on the top, right? So V1 plus V2 by 2 is V. And what is V1 minus V2 by 2? Well, it is omega. I can go over it again. V1 plus V2, I divide by 2 and multiply by 2. So V1 plus V2 by 2 is V. And V1 minus V2 by 2L is omega. So essentially this is the radius. Is that okay? This L is half the track. 2L is the complete track, L is half of it. So theta naught is the initial orientation. This is the circle. We haven't got to the odometry yet. So yeah, here's the derivation for why the multiplier is odd. What if I now put V1 equals V2 here? Well, what is going to happen is you're going to get a 0 by 0 form. But remember how we handled, there was a theorem known as L'Hopital's rule. So if you use that, you'll get the straight line. So the circle becomes a straight line. If V1 equals V2, you can get it from here. You have to use L'Hopital's rule. So now we need a position model. This is the springboard to get the position model. And for that we go to part 2. Okay, so let's get to the next PowerPoint, which is part B. This one, part B. So we have derived the equations for the circle, but we haven't yet forced them into odometry equations, right? Remember, odometry is where I pick up we call them ticks because of the holes, right? It's like those pulses are called tick, 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 right? You count those pulses, so we call them ticks, encoded ticks. So we count them, but we want to know how to take that and convert it into a position, right? That only then you have the full cycle. So that's what this is about. So this method is known as localization through dead reckoning. Just terminology, you know. I don't know why they use the word dead reckoning. You can Google it. Estimating robot position without the help of external measurements. I believe that is the reason they call it dead reckoning. Now, when you use GPS, that's an external measurement, right? When I look up and see a restaurant, that's an external measurement. But here you are counting the ticks generated by your wheel.
It's like counting your own steps.
Like counting your own steps. Basically, it's counting your own steps. And that's why the word dead reckoning is apparently used to convey that you're measuring yourself to figure out how far you've gone. Okay. Now, why is it not perfect? It's because of all these factors, and you may think of something that I've not listed here. Wheel slip. It's very common. So if you have ice, of course, the slip can happen. But slipping is happening all the time. Even on carpet, some parts of the carpet may be more worn than others, right? If people have walked on it a lot, some parts are smoother. And so the wheel that is on that part might slip a little bit. But when it slips, it's going to record ticks, right? But those are not real ticks because the robot did not really move. So that's one of the reasons you could get error. Inadequate resolution. Suppose you just put 25 ticks around the circumference, right? Then 1/25th of a tick is the smallest distance. And that's quite a big piece of tire. So that's going to result in errors, right? Because when you're turning between one tick and the next, you're going to go with the previous tick. Because there's no approximation. You can't say, okay, I'm going to give myself 1/3 of a tick because you don't know when it turned. So obviously there's going to be an error. Uneven tire inflation. It's going to happen all the time. If the right tire is bigger meaning you have inflated it more, and if you drive it on the same and with the same velocity, will it go left or right? Let's assume that you're driving it with the same velocity, but the right tire is more inflated. You'll be going left.
Yeah.
Right? So, how do you know? You're going to go by the text.
Yeah.
So, every day, strictly speaking, you're supposed to check the tire pressure. So, we had the research focusing on this odometry problem, and we always inflated at the beginning of the work day. We have to inflate the tires, making sure they are the same pressure. Wheel misalignment, same thing. We already talked about the IMU. The IMU is used for skid steer vehicles. It can be, both of them can be used for differentially steered vehicles. The picture was here all the time. See, I talked about it, I tried to find a picture, but it's right here. So this is it. See, here is channel A, and here is channel B, slightly displaced. So that tells you whether you're going one way or the other. So we have very creative ways of adding this to the wheel. You know, it doesn't have to be stuck on the wheel. You can just mount it on the same shaft. So you can just put this on the same shaft, and it will spin along with the wheel. Okay, so odometry is coming up. It's the same figure, except we are looking at it from the point of view of displacement. So we assume the wheels have rolled forward just a little bit, just a tiny bit. So delta SR is the arc of the right wheel. This amount of tire has rolled out. This amount of tire has rolled out. The middle point has rolled out by this amount, and the left, obviously we're going left, so the left has rolled out by a corresponding amount, but smaller. And there is the instantaneous center of curvature over there. So everybody familiar with this diagram?
Yeah.
So delta theta, having moved through this, delta theta is the change in pose angle. It's not the absolute pose angle. Whatever pose angle you had here has changed when the wheels came here by delta theta. So your heading has changed by delta theta. Delta S. Oh, SM, S, same thing. Delta S of the midpoint, or S is the linear displacement. So this is the linear displacement. A mix up of symbols here, M, no M, it's the same thing. Okay. Are we familiar with these equations? We've done them before, right? Delta SL. Delta SL is equal to R minus L. R minus L through delta theta, right? So we did this with velocities. Now we are doing it with distances. It's as if the wheels rolled a little bit and we are taking stock. Similarly, delta SR is R plus L delta theta. Delta SM is the average of these two. Now those equations look very familiar, isn't it?
Yeah.
It's V right plus V left by 2, but now we are doing it after we have moved. Where are we getting this delta SR and delta SL? From the odometry. Because it will count those pulses and give it to me. Right? And then I can figure out what delta SM is and what delta theta is. So, right encoder, left encoder, average it, I get this. Right encoder, left encoder, subtract one from the other, divide by 12, I get delta theta. So basically, I can figure out what this is. And I can figure out this angle. So, if I can figure out a circle, I should be able to figure out this point, isn't it? Because if I know the radius of the circle, and I know delta theta, surely I can find out the coordinates of this point. So that is the basis of odometry. And it can be done in such a fine manner, because look at it. You can put 10,000 of these sticks around it. Of course, don't overdo it, because there's a microcontroller counting these ticks. And you don't want to put 10,000. And imagine if you're going at 100 miles per hour, you will make the microprocessor work a lot. So typically in an engineering system, you just put enough money to solve the problem. Anything more, the customer is not going to pay. You're having fun. But the customer is not going to say, oh yeah, I realize you're having fun, so I'm going to give you more money for this product. He's only going to pay for solving his problem. So you put enough text to solve the problem, not double or 3 times that. So displacements are after motion and are measured using encoder increments. So this is why odometry is relative. This is relative to where you were. So now you have to reset odometry again and start again, right? Because you may be on a different circle. Right now you're going this way, but then you may turn this way, and then you may turn this way, and you do very complicated paths. So odometry is only relative. It's with respect to the previous circle. When the previous circle ended, a new circle begins. So you just pick up these little tiny pieces. I took the equations. Remember, these are our basic concept of odometry. So I take this equation and then I can rewrite it. So what's this? X of t minus x naught, right? That is the change in x, delta x. So that is x1 minus x naught, and over here, look at this coefficient. That's basically delta Sm by delta theta. If you look at this, right? Because allow a certain time delta t to go. So V1 delta t is how much the right wheel has advanced. That's basically S for the right wheel. So if I do that, see what I get? x1 minus x naught. x1 minus x naught is equal to delta Sm. So I can rewrite this to the form delta Sm by delta theta. All I have to do is put a dt, numerator and denominator. So V1 dt is delta S1, V2 dt is delta S2, and or right, whichever terminology you want to use. V1 is the same as R, V2 is the same as L, and then I can rearrange the odometry equation to this form. So that's it. Delta theta is generated by calculations on the odometry. Similarly, delta Sm is from the odometry, and I can write the new position. So I'm saying I've got this much extra x and extra y. And then I say, okay, I start again, new circle. I've got this much delta x and delta y. So you keep on building, each successive odometry reading, you assume there's a circle because you're taking the odometry equations fairly frequently. So you assume that you have to update and then start again. Right? There can't be one big circle anymore. There's only little tiny circles. So between one odometry reading and the next, you push it up using this equation. And then you do it again. Your x1 becomes x naught. Do you know what I'm saying?
Yeah.
That once you've calculated x1, it becomes your new x naught.
Yeah.
And then you proceed little tiny steps. It's literally like steps. It's like counting your steps. Okay. So this is the Ackermann steering. So this is the principle on which the steering for a regular car is designed. So in MATLAB, you have a model for a car with Ackermann steering. Now, what is so special about it? So a car has 4 tires, right? So let's say that these are drive wheels, rear wheel drive. Okay? And now, right now it's engaged in a turn, and the center of the circle is right here. Similar to the differentially steered vehicle, you have an ICC, which is right here. Right here. So, you notice something about the front wheels? So the tires cannot be parallel. Now, Henry Ford's car, way back when, probably Ackermann came later after that. We can look it up. Ackermann, this is called Ackermann steering. I believe the person is a person. He probably had the original patent for it. So he discovered that you can't have these tires parallel. You know why? Because think about it. This tire is closer to the center of turn, the ICC. That tire is further out, right? If they were parallel, then one of them would be dragged on the ground when you turn. Because this is on a shorter circle. Can you see? Yes, both circles have the same center, but this one is on a shorter radius. That one is on a longer radius. They cannot be parallel. If they are parallel, you'll be dragging the tires. And as I said, probably the first cars, they didn't care. They were just happy to have a car. And so they were dragging the tires. But then Ackerman came up with this mechanism, this thing here, it's not electronic, it's a mechanical arrangement. This linkage keeps those two pointed slightly differently. This one has to be slightly out. This one the left front tire has to be slightly in. That's the only way you can roll. So he realized that and he came up with a patent, must have made a lot of money by, whatever was rich in those days, he probably made a lot of money, unless he was working for a company, in which case, the company gets the patent. So that's it. That's the basis of the car. Now there is one vehicle that we all have driven at some point, maybe still drive, that is very similar to Ackerman steering, except it doesn't have 4 tires. It's the bicycle. So the bicycle model is also available in MATLAB. So if you don't want a sophisticated car model, sometimes people use a bicycle model to get some ideas resolved, and then they move to the car model. So it's exactly the same thing, right? You tilt the steering wheel and then you pedal, right?
Yeah.
But except that you have to balance, it's kind of similar to a car. The Ackerman is not relevant because you don't have 2 tires. So, all the possibilities you would not believe. So let me first take you through the meaning of the shading here. So the shading indicates motorized wheel. That means it's a driven wheel. If there's no shading, then it is unpowered. It's just coming along with the rest of the vehicle. So here is an unpowered wheel. There is a motorized Swedish wheel. We'll get to that. Motorized standard wheel. All right. And then you have a steered standard wheel. You see those 2 things sticking out? It's a steered standard wheel. And so on. You get the idea?
Yeah.
So you would be surprised, how many different architectures can be created. So that's the first page. So this is a bicycle. Agreed? Driven back wheel and a steerable front wheel. This is a differentially steered vehicle, only 2 driven wheels. How is that possible? Would it fall over? Well, you don't always need a caster, because if the center of gravity is very low, right, then a 2-wheel vehicle will be stable. If you put a center of gravity above the wheels, it's going to fall over. But if it's weighted so that the center of gravity is below the 2 wheels, you can have a stable 2-wheel differentially steered platform. So that's what this is. Now this is the regular differentially steered vehicle, 2 driven wheels, a support wheel, caster, or it can also be a spherical wheel. The problem with this is that it is asymmetrical. So maybe if you load too much in the front, it might tilt over. So you can add another caster if you want. Now here's another differentially steered wheel with a caster or spherical wheel at the back. You know what the problem with this is? Now the pivot point is here. So when the robot swings, that whole tail is going to come like this, right? So over here, the footprint is circular. So when it turns, then the footprint is going to remain on top of itself, right?
Yeah.
But this one over here, the whole tail. So you have a problem. So when you're turning like this, and maybe you have a traffic barrel here, you're going to knock the traffic barrel because your tail will come out like this. So that's why some people don't like this. They like the axle to be in the middle, but then it creates a need for maybe a 4th wheel. This one is fine with 3 wheels. That one might need an extra wheel here. So those are the trade-offs in design. This is like a front wheel that is driven and steered, and the 2 rear wheels are unpowered. See, you can have the front wheel driven and steered, or you can have it the other way around. The rear wheels are driven, the front wheels are steered. So you can see, right? Different architectures. There are many of them. It goes on and on and on. Yeah, that's the Ackerman front wheel drive. That means the powered front wheels as well as the Ackermann system. Some of them are actual robots. Charlie and Capera, the actual Nomad, they are actual robots that are being sold. Probably no more. And this is an interesting system. Both the wheels are aligned and you have the 4 corners being supported. So we have built some of our own robots. You're going to see them now shortly. We built our own robots because we started this in 1995. And we had students, and a colleague of mine is very good with his hands. He's an electrical engineer, but he's more a mechanical in the way he thinks because he grew up on a farm. So he learned how to use tools and everything. So we used his ability to build our own robots. 125 kilograms at a time, quite big, you'll see them. So all the different architectures, this? So this is known as an omnidirectional vehicle. It can go any direction at any time. Have you seen this computer chair?
Yeah.
So you can slide it, right? By putting your foot on the floor and pushing off, you can go in any direction because the casters, they align immediately. So there are robots with this architecture, except that these are powered caster wheels. You can make them, you can put motors there and power them. So then you have an omnidirectional vehicle. You know the advantage of that, right? You can steer in any direction. But I also told you the danger of them. Human beings are not very good at driving those vehicles. You give them too many degrees of freedom, they're going to kill somebody. So that's the danger of coming up with a vehicle with caster structure. So this is omnidirectional. This is your standard differentially steered. The beauty of this is, yes, it's not omnidirectional because it cannot go sideways, right? But if you're patient and you turn around this way, then you can go sideways. So it can't go sideways instantaneously, but if you're patient, you can turn and go. So in a sense, it's much better than this because it's easier to control. This is very hard to control. And that's your tank, skid steer. You can have tires or you can have tank treads, they're both skid steer. So no configuration is satisfactory for all aspects. So this is the pain of engineering, also the beauty of engineering. No one product does everything for you. So therefore, that's where the engineer comes in. You find what is needed for this mission and you design the robot. The Mars rover? That costs millions of dollars by itself, the Mars rover. So you won't build cars like that because, what will you do with it? But it's got 6 wheels, 3 pairs. Each wheel can go up and down relative to the previous pair because they expect that you'll have to go over some Mars rocks. So they've designed it so it can go like this as well as this way. So it's a very sophisticated vehicle. So maybe if you want flexibility, you need, so basically when you make a decision, it's trade-offs, right? What are you looking for in this vehicle? An SUV is not the same as a small Maruti. An SUV costs you more because it has more clearance, right? So trade-offs is what you do in engineering, but you can have an adaptive design. That is like a compromise. So you've seen in these movies, movies often give you a look into the future. So you've seen in the old James Bond movies, a car will suddenly become a boat. So if you have an adaptive design, then you can tackle multiple challenges. But it's costly, right? Cost is always there. So let's go through these. These are all the vehicles we have worked with at the University of Detroit Mercy. So this was our very first vehicle. Somebody was throwing away a golf cart, and at that time we were so poor, we said, give it to us, throw it in our direction. Look at it. Can you imagine? That monitor, you guys are too young. You probably have never seen one of those, but the monitor is deep because it's a cathode ray tube. Probably it's under the ground somewhere, all these monitors, they've been removed. This is a compressed gas tank, compressed air tank, used for emergency braking. So if you go to the competition we go to, there has to be an emergency brake. So there has to be, here, see here? So in other words, if the autonomous vehicle starts running away from you, the judges want to be sure that you can run and hit that button and kill it. So what we do is, this tank releases air and we literally have a brake, like a human foot, that applies the brake. So it was our design at the time. We had fun doing it. It did work well all the time. And you can see this massive computer and all the circuitry everywhere, because at that time there were no control units for pulse width modulation and so on. So we did our own. So this is no more because it's been chopped up and thrown away. Okay, so this one is the old wheelchair. So it's got a payload. The competition requires a 20-pound payload to be carryable. So we have to create a payload space because it tells you the dimensions of this block and it has to be on it. So you can see it has some cameras. Also notice here, this was our wheel encoder. We had a small wheel rolling on top of the big wheel, right? So do you agree there's a fixed ratio between the rotation of the big wheel and the small wheel?
Yes.
And our encoder was actually mounted here. So by reading the small wheel, we are able to figure out what the big wheel is doing. So students have a lot of fun with it, right? With a joystick, you need a joystick because it's autonomous during the competition, but then you have to take it there, right? Because it's not that autonomous that it can automatically find the starting position. So we just steer it there and then we let go and then it becomes autonomous. So the picture, it doesn't look that good, it looks much better here on my screen obviously, but there it's made it. So this is the same wheelchair, we turned it around. Here we are running it forward with the caster wheels. Here we are running it forward with the big wheels. And notice we added 2 tires here because the competition has a sand trap. And the first year, once we got into the sand trap, it started spinning. It did not have enough traction. So we added a second wheel for support. So there are 2 wheels here now. And those days we were really, really poor. We did not have money for a LiDAR, so we had ultrasound. See these 5 ultrasound units? So ultrasound is much cheaper, but ultrasound only tells you whether there's an obstacle within this zone. LiDAR, pretty much, the zone is like this, 1 degree, right? Ultrasound is about 30 degrees maybe, and it says somewhere there is, an obstacle. So we have to put 5 of them. And so by overlap of the 5, we can narrow it down. So we had 5 of them and overlapping zones, and we can roughly figure out where the obstacle is. Not as good as the LiDAR, but $30 each. LiDAR at that time was like $1,500. Now it's come down. So we have a camera we created our own lane lines. The floor looks pretty bad because they were stripping it to repaint it. And that's our team of students, like part of it. So this was the new wheelchair. So it had a steering wheel, but we removed the steering wheel because autonomous means that no human being steering it, even if it's very small and hiding underneath, the judges will see them. So we took out the steering wheel and then we created a chain to grab the steering wheel like a human and steer it. So the computer was giving directions on steering the steering wheel shaft. So before it was a manual shaft, but now there's a chain going around that is steering it. So that's my colleague that I was talking to you about. He's really good with mechanical. A story just to relieve the tedium of constant talk. So he got his master's at MIT. And one Christmas break, he made the mistake of going home to Michigan to see his family and wife. When he came back, there was a note stuck saying, all your stuff in the lab, right, is packed up in this box. Just turn in the keys to your laboratory. Yeah, because they don't expect you to go home for Christmas. So they work constantly. The divorce rate amongst MIT professors is the highest in the world. It's like, because there's no family life at all. So probably more than 50%, 70, 80%, because they basically live in the labs. So when he came back, he found his note and he was kicked out of that group because he went home for Christmas. So this was the vehicle we had a lot of fun with. It did not work because it was It's called it's an omnidirectional vehicle, at least our attempt to create one. So it has 3 computers. I think right now there is only 2 of them on board. You can see it looks like a camera and LiDAR. See, this is the big LiDAR of the early days. So what this is it's capable of going in any direction at any time. The way it does that is these 3 sets of wheels. So there are 3 of them, pairs. 1 pair, 2 pair, and then the 3rd pair symmetrically located. So we turn all the wheels in one direction. Get it? We turn all the wheels in one direction, then we go in that direction. But if you're going in that direction, then you also have to see in that direction. So what happens is, when these wheels rotate, the upper platform also rotates with it. So complicated mechanical architecture. As the wheels rotate, the upper platform also rotates, so that your eyes are always facing in the direction of motion. Very complicated mechanical design, but you also have mechanical implementation. Things have to be manufactured properly, and we had students from the ME department also on the team. It was a joint project. They didn't do a very good job. So often it happened that the wheels turned, but the upper platform was still facing this way. So it's like I'm going this way, but I'm still looking this way, which is an odd way to navigate, right? So something happened, the gears, the chain slipped because they didn't design good fixtures, and we ended up by not doing very well in the competition. And this is where we got really professional. This was our first really solid vehicle. So this is a 2-body vehicle. It's known as an articulated vehicle. So this is the front and this is the rear. There is a link here. See the link here?
Yeah.
And it can pivot. So there is a pivoting joint here. So basically, remember I said that if you have a long differentially steered vehicle and you turn, the tail will whip something. So here you don't have that problem because only the front pivots. The tail stays in place until you're ready to move. Then when you move like a train, it drags the tail through it. So you see one computer here. You see, always you have to have an emergency stop, GPS, LiDAR here. So the cost started to go up, probably $30,000-$40,000. So here is our first traditional differentially steered vehicle. That was an upgraded version. These are 2 different vehicles. This is the competition course. You can see the lane lines here. Not very easy to pick up. My colleague, the MIT guy, he got his master's and PhD in image processing. So he was responsible for guiding the students on how to pick up these lane lines. Now everything is machine learning, deep learning. You don't need to know anything, by the way. You don't need to know anything about image processing anymore. Everything is machine learning, which I don't believe, but that's what they are pushing. So an interesting story about this guy, He was writing apps for Android. So this was after he graduated, and he was saying that, he wrote an app and then he got a $20 check, and then next week he got a $20 check, and then the checks started to get more frequent. He started getting $50 checks because people were buying his app. And before you know it, he had made $1.5 million on it. That was his first app. And I can bet you that he's probably a multi-millionaire. Just a brilliant programmer. He started programming at the age of 4 or something. So often, through computers, you would have 2 keyboards and you'd be programming like this. And there were other students in the team who did not have half his skills, and they would be telling him what changes to make to solve the problem. So it was quite funny because he had this ability to shut out all noise, that he won't even say get the hell out of here. He would just continue programming. So he was responsible for our series of successes in the competition. So that's not the vehicle we built. This is from ClearPath Robotics. It's a platform we bought and then we built up on top of it. You can see this is an engineering building here. So this is a commercial chassis, because typically there's no real need to build your own chassis unless you're trying to teach the students something. You can just buy a platform, like the self-driving cars, they're not creating the car, they're just grabbing a standard car and trying to make it self-driving. There's no need to create a car for that, right? So this was a chassis that we purchased. Okay, and this was our most expensive chassis, about $84,000. It's a Segway platform, and it's got a 3D Velodyne LiDAR. So a significant part of the cost is because it's a 3D LiDAR. So a 3D LiDAR, unlike a 2D LiDAR which can only see in a plane, a 3D LiDAR sees everything. So you can actually, I think at the very first lecture I showed you like a 3D LiDAR separating the road surface from the side of the roads. So a 3D LiDAR has the ability to pick out the road surface. No, you have to do perception. It's not just in the data. You have to write code to get that information out of it. But you can separate the road surface from the side of the road. So 3 computers, LiDAR, stereo vision camera, GPS, compass, IMU, it all adds up pretty fast. The platform itself was about $35,000, the Segway platform. They sell it, you know Segway? Yeah, so it's a very popular vehicle. It hasn't caught on as much as the designer thought, but it's still very popular on campuses, you know, for campus police. So it's about $84,000. So that's one of the vehicles sitting around now and unused. So we used it for one competition, but after that it's just sitting. It's been stripped, like we have taken the sensors off it, but the platform itself is unused. We can still, the platform is still good. Yeah. So I won't show you these videos because you know the Segway is auto balancing, right? But not really, because they don't give you all the details. We bought the platform, they promised us something, but a lot of it is proprietary. So if something is not happening, they'll say, okay, bring it here, you know, we'll fix it. But they won't tell you on the phone how to fix it yourself. They don't want to reveal their algorithm. So it turned out that we had to figure out how to balance it. And then after a while, we said, why are we making a balancing vehicle? We are trying to make an autonomous vehicle. Why are we diverting half our resources to making it balancing? That's like the product. Remember I told you, don't put things into the product that your customer doesn't need. So we created another extra wheel here. Can you see here? So no more need to balance. We just said to help with the balancing. So there's the extra wheels. It moves much better now. Earlier, our control algorithm was causing it won't fall over, but it was going like this. And we had a heart attack every time. Our control algorithm was making it go like this. Now, no more balancing problems. So we have a differential GPS, you can see. Much more accurate. So this is a skid steer vehicle, 3 tires on the right, 3 here, 2 tires. So if you want to turn left, you spin the right tire set faster than the left tire set. So this was a project actually that same student who is a multimillionaire now did, during his college days, gathering a bunch of coke cans and delivering it somewhere. So walking robots have better maneuverability in rough terrain, right? So why are we interested in designing robots with just 2 legs? Because balancing is a problem, right? That's because when you have 2 legs, you are capable of moving on rough terrain much better than on wheels. See, a regular wheeled vehicle would find it hard to get to the top of Mount Everest because it's just not possible. An SUV is not going to make it very far on Mount Everest. So when you have legs, you're able to climb, right? But wheels have an advantage on flat terrain. No matter how many legs you have, you cannot keep up with something on wheels. So that is the compromise I was talking to you about. You have to figure out what you want. So is there an adaptable solution? It turns out in the university research community there is. So somebody did come up with this. It's called a shrimp, I believe. So look, it's climbing, it's also rolling, but it's also climbing. So it's becomes like legs. The wheels become like legs, right? Remember I showed you in the first lecture, there are some vehicles that do that, right? You can go backwards up stairs, but you can also roll for handicapped people. So essentially, that's what people who are innovative, they try to come up with a solution that is different, that enables handicapped people. Did you check whether your launch file has those patched commands or not? Remember I showed you some patches this morning? So the way to do that is to go to that particular launch file and use gedit to open it and see whether you have. So let's do that right now because that is critical when you want to use the Turtlebot 3 simulated version. Is these lines, if they are missing, you're in trouble. So what I want you to do is, I want you to open your, 1 second. So do you know where this is? Have you ever explored your Catkin workspace structure? So you need to go deeper and deeper. I'll show you. Let's pull this to one side. Kill this and get back my gazebo, or rather here. So you can browse like we used to do in the old days, or even now we do on our PC or Mac. So where are we? So I'm in the Turtlebot 3 workspace because I like to keep my robots in separate workspaces, but you're probably in the Catkin workspace. So go down in your Catkin workspace, and then the SRC, and then the Turtlebot 3 simulations, and then the Turtlebot 3 gazebo, and then here is the launch directory. And there is the empty world. Now, you don't need gedit because I believe if I double click on this, it will use gedit. And here it is. So you see here, insert these lines in the original package. So that was the patch. This, I need you to check to see whether this patch is inserted there. Right before the tag launch, the end tag. So this is the end of the file. So you need to see this. Can everybody check? Insert these lines in the original package. That's my comment. This is how you comment in some Linux files. If it is there, fine. If not, you'll have to grab those lines, which now I'm reminded that I need to post it for you there. So let me pull it down from the other course and get you to access those. So let it download. So download. Okay. Good. Then I download. So now I'm going to upload it to your course directory. So I want to create the right directory structure. I'm a bit over organized, but I can't help it. It's too late to change now. So I say, so I'm creating the software environment, and then I'm going to create the patches directory here. So patches, software patches. No, it's not one, because I have another copy of it. That's why it labeled it as one. I'm going to remove that right now. This one is done. I don't want the one there. Rename it. Rename it. File or folder can't start or end with white space. No, doesn't have white space. Okay? So you have everything there. So check that this patch is in there, or if not, you can either put the patch in or put the whole file. You might need permissions, I told you. If it's a write protected file, you have to do it using sudo or something. So it's got a house. Here's a house. And then it's got other things, multi-robot launch. See, many Turtlebot 3. Turtlebot 3 world. Okay, so let me just set up for what I was going to show you earlier. Something happens, when I do that color change. Sometimes it works, sometimes it doesn't. Background color.
go to other locations. Other locations, then you will find computer. Other locations, first go to other locations, then go to computer, then go to opt. Opt. Did you find that opt? Other locations, you can find opt.
Oh, I see.
This is the other packet.
You are in a different packet. I'm sorry.
That's why
My
we got
installation is
some
slightly
contact.
different from, so it might be the case for you also.
Sir, actually this is the native Ubuntu and I did the same way as you do. But this is like, I don't know, maybe MATLAB made like this. Their package,
Yeah.
something different.
Right. So my configuration is slightly different.
Yeah. Okay. Then, okay, opt. Then go to ROS. ROS. That's like we source, you know, with what?
Because when I follow the tunnel about robotics,
Yeah, now
it comes like this.
Then go to Noity. Noity. Go to Noity.
You can't see it in the op.
After the Noity, go to share.
Yeah, see? Let's go on, share.
Share. Then you will find the tunnel board 3 gazebo.
Tunnel about 3%. Got it?
Go down.
And then you need some pseudo. There you definitely need pseudo privileges. Here it's underneath my directory. So I might not.
Yeah, there you can find the launch folder. Then everything is there. Can be world, what, something, house. Everything is there.
Will they need pseudo privileges?
No need, right?
No need?
No need.
Okay.
No, you can just see how can we trace.
No need. Okay.
Then you can find the launch folder. Yeah, then you can directly replace it.
Now, you need to understand this circle program completely because I'm going to give you a task which is, we're going to do a cursive script. So do you think you can modify the circle program, call it something else, keep the circle program, but when you modify it, save it as something else and create this. Or you can pick something simpler, maybe this. You can find something that is simpler and try to implement it. Now how are you going to do this? Let's see. So, you know how this works, right? RTT is being tested against the total time to drive. So for this, you don't have one circle, you have several circles. So you'll have a for loop outside this while loop, right? And the for loop will be driven as many times as you have circles. For each one of them, you have to calculate how long you want to drive. So that's just guesswork. Okay?
Yeah.
And the inside while loop is going to implement that portion of the circle, right? And then when you come out into the for loop, it's going to take the next one. So technically, the odometry, you'll have to adjust. You have code there which shows you how to accumulate the odometry. So just accumulate the whole thing. And when you plot it, it should look like this or something close to it. Doesn't have to be exact. So, I'll give you an example. So maybe I go half a circle this way. Then I go straight. I'm just going to go straight. Or maybe a circle with a very large radius, right?
Yeah.
Then I do another circle. Then maybe another big semicircle. Just make it rough. And then finally maybe a quarter of a circle. So set up the loops, you can put crazy numbers and then you can adjust it. So maybe 4 or 5. So 1, 2, maybe a 3 and a 4 or a 5. To give it more shape, maybe you need 5. So see whether you can do it, because then you will really understand this particular MATLAB program, and then it'll be a platform for what we do next, which is we'll take up the controls issue, open loop and closed loop control. We still have to do that. So when you run a program, you go in with an idea of how to do it, right? Then you implement that idea properly. What many people miss is they miss the step of implementing the idea. Properly means the computer should be doing what you want it to do. Many people think, because I know what to do, the computer will know what to do. No, that's where the biggest jump is, right? You have a gap. Because for human beings, we understand each other even when we make mistakes in the words and the sentence and so on. Computers are very dumb. You need to be extremely precise. If you are thinking angles but feeding radians or the other way around, it doesn't know how to solve that problem. It assumes that's what you want. So you have to figure out the radius of the circle, how long you want to go around the circumference, right? And then each while loop has to be driven by a new RC or whatever you call it, TC. So you'll have a TC for each piece. So you should be able to do it. The idea is to get a rough figure and then you can shape it. So if you say 1/10 of the circumference, then you calculate it as what? 1/10 of 2 pi r divided by the velocity you're using. That's the time to hold the circle. All this is open loop control because time is being used for getting distance.